complex numbers. So term 4 is a pretty short term. There are 5 weeks. 5 weeks is basically what we've got to get through this unit. I'll just pause for a second whilst we... So complex numbers is just chapter 7. We will be using our blue book there. And it's going to start off reasonably straightforward, but it is going to be some new notation for us. So it's going to be some language that we haven't heard of. And that's why I've inundated you with these sort of 2 pages of text, so that everything that we need to answer in 7a, we're going to be referring back to these questions here. So you've seen me use Z a fair bit. We were doing it when we were doing polynomials. Polynomials, PMI. So Z is a set of integers, and an integer is a whole number. And that means it goes from, minus 100, minus 99, 0 is an integer, and then all the positive integers as well, all the positive whole numbers, 1, 2, 3. Okay, so we have the set of all integers. We have the set of positive integers, okay, where we just consider positive values. We can have the set of negative integers, where we just consider negative values. All right. We also have the set of natural numbers, which they call the set of counting numbers, and they're not different from the set of positive integers. Okay, so if you've got an n or a z plus, they mean the same thing. We tend not to use natural numbers because it's different people use it differently. Okay, whereas everyone means the same by this language here, z as an integer. Okay, so we've got natural numbers, the set of all integers, the set of all positive integers, and the set of all negative integers. We have Q is all rational numbers. So we know what rational numbers are. They are numbers that can be expressed using a fraction. It can be expressed as a ratio. So that's the set of rational numbers. And then Q prime, or Q dash, okay, is a set of all irrational numbers, the numbers that can't be expressed as a ratio, and they're numbers like root 2 and pi and so forth that have an infinite number of decimal places. And then we have R. Okay, if we're talking about a real number means any number that can be expressed on a number line. Okay, so if we think about a number line, and particularly in between 0 and 1, there are an infinite number of real numbers between these 2 points. There's an infinite number of real numbers, okay? Because you can keep adding decimal places, you can keep dividing that fraction up, or that interval up infinitely. So there's an infinite number of real numbers between these 2 points, okay? So when you think about these sets, right, if you think about which set's bigger, the set of integers or the set of real numbers, okay? So the real numbers is every number that can be represented on a number line. The set of integers is only the whole numbers that can be written on a number line. So it's like which set is bigger? When we say set, that means a group of numbers. Which set is bigger? Well, clearly the set of real numbers is bigger. Okay? The set of real numbers is bigger. So let's look at some more notation that we're going to use there. And that is, we would say that the set of integers is a subset, okay, of the real numbers, okay? That this set is a part of this set, but it's a smaller part of it. All right, does that make sense? Okay, so then we've got closed and open intervals. So that's just going to be those sort of 3 terms there we can come back to when we're asked about it at the end of our example. And then we've got interval notation, and that's what we're pretty familiar with already, okay? So interval notation is this, isn't it? All right. So if we want to write something in interval notation, this is how we express it: -3 being less than x being less than 7. Okay. And what we're introducing you to today is set notation. All right. And so maybe you can already see how those link up. Okay. If it includes the number, we use a square bracket. If it does not include the number, then we use a rounded bracket. Okay. Now, when it's described like this, if I'm saying -3 all the way up to 7, what that means is the default assumption is that it's all real numbers from -3 all the way to 7, but not including 7. Okay? So we can have it written like that. That's what we're familiar with. This is what we're learning today. And here's a way we could represent it on a number line. If it says this set, but where the numbers are integers, okay, then all of a sudden it's not a number line, it's only including whole numbers, isn't it? So it's going to be -3, -2, -1, because it doesn't include the numbers that occur in the middle and in between them. Okay, let's flip over the page there. We can have intervals that overlap. So that's pretty well illustrated by this diagram. I'm going to bring it up here on the board so we can talk about it. So if we're going from -2 to 5, okay, from -2 to +5, but not including it, and we're combining that, okay, the union of this set with this set from 1 to 7, then the set that you get when you combine them extends from -2 to 7, okay? And then we have some more information about the notation. I've already pointed out some of that up here for you guys. But here's a good example of what we mean when we say union of sets and so forth. So let's read through this. We've got epsilon means is an element of, I've told you it belongs to. All right, so for instance, the number 2 belongs to this set, 1, 2, 3, 4. It's a part of it. All right, 2 does not belong to this set here. Okay, so we have epsilon with a line through it. The union of sets. Okay, so if we have the set 1, 2, 3 and we unite that set with this set, then the new set that we get out of that is 1, 2, 3, 4, 8. Where do these two sets intersect with one another? What's the cell that they have in common? What's the element they have in common? 3. This is a subset. Okay, so 1, 2, 3 is a subset of 1, 2, 3, 4, 8. But this set belongs to this set. That this small set is a part of this one. That's what the sort of idea I'm trying to get at over here. The set of all integers is a subset of all real numbers. All real numbers on a number line. Integers are on a number line, but they only take whole integer values. Okay, and we have we have superset, so that could be the opposite. You could write it. We could write R is a superset of Z, so similar to our interval notation. And that's sort of getting a bit beyond what we need to do. And then we have an empty set, a set with nothing in it, no numbers in it. Okay, so let's get into our example then. We have from -3 to 7. All right, and it says, list all of the elements, okay, list all of the elements in this set if the elements are integers. Okay, so all of the integers between -3 and 7. So for part A, that's going to be -3, -2, -1, 0, 1, 2, 3, 4, 5, 6. Why didn't I put 7? It's all the way up to 7, but not including 7. Okay, so the highest it goes to is 6.999. That's not an integer, so we're not including 6.999. All right. Now it may pop up in the textbook. Find A of n. That means how many numbers are there in this set? How many elements are there in this set? And if you've listed them, you can just count them. We've got 4 and 6. We've got 10 elements in this set. Okay. All right. Part B says, list all of the elements if we're only considering positive integers. Okay? So here's the set with all the integers, okay, because integers can be negative numbers. What's the set if we only consider positive integers? Well, that's this part here, 1, 2, 3, 4, 5, 6. 0 is an integer, but it is not a positive integer, so it does not belong to the set of positive integers. Okay, part C. Which of A or B is the subset? Okay, so let's call this set B, and let's call this set A. Okay, which is the subset? Well, let's write an expression. This set is a smaller part of this set, isn't it? Okay, but this is a bigger set, and it includes all of set B. So what we should say is, we could write it two ways. We could write set B is a subset of set A. Okay, or we could write set A is a superset of set B. Alright, so that set A is more powerful, more large, it encompasses set B. Okay, write the set in interval notation. So we've done that here, that's part B. -3, less than or equal to x, less than 7. And then part E, is the set open, closed, or neither? So let's refer back to our notes here. Okay, closed and open intervals. An interval is closed if both of its endpoints are included. Okay, well we have -3 included, but 7 is not included. It's open if both of its endpoints are not included. Okay, well we don't have that either. So this set is neither open nor closed. Alright, what if it said, if we consider the set like this, where we said where x is an integer, okay, we saw that there were 10 elements to it, okay? So there's a finite amount of elements in the set, alright? What if I said, how many elements are there if x is a real number? Okay, x can be any number between -3 and 7. So it could be -3.15 zeros and then a 1. Okay, it could be -2 and then 72 zeros and then 195. So what's the point I'm getting at here? How many numbers are there if we're considering real numbers? There is an infinite amount. Okay, so if we're not given any definition, if we're just told this set, we assume it's real numbers. Over here in the example, I was very specific. We're taking them as integers. I said, here's some notation. When they're integers, how many elements are there? Okay. If we're not told anything, then between that, there's an infinite number of integers that can occur in there. All right. So maybe tricky because it's new notation. All right. But all the information is on the pages there. So let's work through 7A. That's our plan for today.